A lot of things that happen in the real world repeat at regular intervals. A lot of things that happen in the real world repeat at regular intervals. A lot of things that happen in the real world repeat at regular intervals. How are we going to model this? And there, just to name a couple: tides, phases of the moon, tax planning, your heartbeat, you hope, hormone levels. There are just tons of examples, and we need a way to model these. We need an active function that's going to model these things that we observe. Luckily, we have a really nice function that does this. The function's called Sine, S-I-N-E, and you don't have to calculate it. You have to understand its properties. So the first of its properties is, and here's why you don't have to calculate it, is built into virtually every calculator ever built except for the credit card size ones they give you as freebies at a bank. There it is, Sine. It, in fact, is so useful that it is built into Google. So if you want to know something about Sine, what you can do is go into Google, and I've typed in a particularly nice version here. It's got a few terms, and but there it is, and Google will graph it for you. And one of the things that this picture proves is that, in fact, you can use sines, if you combine them, to cover almost any periodic phenomenon. So these are useful functions. They're easy to get at. You don't have to calculate them. You can't calculate them. And it takes a machine to calculate them, or a slide rule. And so that's what we're going to have. The graph is pretty easy to do if you keep a couple of things in mind. There's a trick to it. The first part of the trick is to draw this grid, 4 squares on top, 4 squares on the bottom. You can see it's kind of rough. That's okay. The extent here is one period, one cycle, one repetition. And it works out that with the sine function, you start at 0 and you work your way up to 2 pi, which is about 6.28. And so there's where the graph starts. So I'm going to label those points. It's fascinating why pi comes up with the sine function, but that doesn't help you do the applications. What helps you do the applications is that Google thing I showed you before. Okay, sine starts at y equals 0, and it ends at y equals 0 because it repeats. So if you're at y equals 0 at some point, 2 pi later you're at y equals 0, 2 pi later you're at y equals 0. It repeats. So there's where y equals 0 is on the graph. And I'm going to divide this into the 4 pieces where x is. And I'm also going to illustrate my reluctance to simplify things. What you do is you start at 0, you go to 2 pi over 4, then you go to 2 times 2 pi over 4. Normal people say 4 pi over 4, but that doesn't help you at all. Then 3 times 2 pi over 4, and then 2 pi again, or else you could say 4 times 2 pi over 4. Anyway, and then you can draw the graph of the function, and it is remarkably easy to get a reasonable graph without too much effort. So that you first start in the upper left quadrant, and you draw a curve that looks something like this. It starts out almost like a line. That's important. When we do some more calculus, we'll figure out why that's the case. But then at the top here, it's horizontal. So it starts off like y equals x, and then at the top it's horizontal. In the next square, you have a symmetric mirror image of that. So at this time, it's going to start out horizontal and end like y equals x. So that's going to look something like this. It's not going to, it already does look something like that. Nice and symmetric. And the second half just happens below the x-axis, starts off like y equals minus x, ends up horizontal, and then starts off horizontal and ends up like y equals x. So there it is. And then the sine function repeats and repeats and repeats and repeats. And so there's the deal. Now, that's not how these come up in real life. If you want to look at tides, or the moon is on like a 27.4 day cycle or something, the period isn't 2 pi. If you want to look at electricity, in this country it's 60 times a second. In parts of Europe it's 50 times a second. Who knows what it is on Venus, because they count differently on Venus. And so the one thing that you can do is use the transformations that got covered in pre-calculus to change this. You don't change the graph, you just change the axes. So first thing I'm going to do is I'm going to change x to, let's get the notations right, let's call this x over p. I'm writing out the function that I'm graphing one piece at a time. Now you know that if you divide x by p, that stretches things out. That makes, so now the period is 2 pi p. So this now becomes 2 pi p. The next thing that you can do is you can shift things. Remember, when you subtract something from x, that shifts it in the positive direction. When you subtract something from y, that shifts it in the positive direction. So I'm going to shift it by something that I'm going to call S for shift. So that makes this spot x equals S. And then you can take the sine, and so you know what that looks like. The shape stays the same, it's the axes that change. That's an important part of doing any of the basic graphs. So I'll sketch that in. There it is. But now you've got a different x-axis. The x-axis is here, and so forth. The next thing that you can do is multiply by a constant a. Now, if you do that to y, that's like dividing y by a. You stretch, and so what that means is that this distance here, the distance from the baseline to the top, is a. And finally, you can add a bias to it, so I'm going to call that plus b. And so this is where y equals b. So let me label a couple of more of these. And so here's this complicated sine function. It's been shrunk, it's been shifted, it's been shrunk again, it's been shifted again. The shape doesn't change, it just what changes is how you label things. And this trick, this is not a trick, this is an important method that works with all of the basic functions. And so this is how we're going to handle sines. You can study all the exotic properties. They're wonderful, I love them. But what we need to know is that sine repeats, and we can adjust it, and we can add sines together to get almost anything interesting that repeats. And that's the story on the sine.